what we're looking at here is the 2007 Mechanics AP Physics test, question number 2. And this question states that in March of 1999, so probably before you were born, the Mars Global Surveyor, it entered its final orbit about Mars, sending data back to Earth. Assuming a circular orbit, which is so nice for us, with a period of 1.18 times 10 to the 2 minutes, which I never want to use minutes, so I'm using this here, 7.08 times 10 to the third seconds, and an orbital speed, for that circular orbital speed, of 3.4 times 10 to the third meters per second. We know the mass of the Surveyor is 930 kilograms. Probably won't matter in the end. For most of these kind of orbital problems, the mass of your satellite, your orbiting object, never matters. And the radius of Mars is 3.4 times 10 to the 6th meters. What we'd like to do for part A is calculate the radius of the Surveyor's orbit. So, how can we go about doing this? Well, let's do this. Let's draw the red planet first. There's the red planet. There's its center. And our Surveyor is out here at some position. I don't know what it is. A full distance r away. And it's making a nice circular orbit, perfectly drawn by yours truly. If we want the radius of this orbit, and all we have is a speed of 3.4 times 10 to the third meters per second, and a period, which is a time. We know how long it takes to orbit the planet, 7.08 times 10 to the third seconds. We can actually go back to kinematics and kind of figure out the radius of the orbit. Normally in kinematics, we would think that a distance can be thought of as a velocity multiplied by a time. But in this case, we're not looking at a linear distance, we're looking at a circular distance. So how can you get how large this distance here is as you go around? Well, that's a circle, and you know the radius of a circle. So this radius of the circle is just 2 pi r, where that r is the radius of the orbit. So we can just say here that this is 2 pi r, the radius of the orbit. And this has to equal the velocity, which was 3.4 times 10 to the third, and the time, 7.08 times 10 to the third. And all we have to do now is, oops, we just have to solve for this r value here. That's all we have to do, which is really nice and easy. We'll just divide each side by 2 pi to get rid of it, and we will find that our r value here, it equals that velocity, 3.4 times 10 to the third, times the time, 7.08 times 10 to the third, divided by 2 pi, and that gives us an orbital radius for our satellite of 3.83 times 10 to the 6th meters. You can check if this answer is right or wrong very easily. It is times 10 to the 6th meters, 3.83, and the radius of Mars is 3.43 times 10 to the 6th. So this radius is larger than the radius of Mars, which means it is orbiting the planet. If we had a value less than the radius of Mars, we'd be into the planet, which means we'd be destroyed. So this is nice. It's a good answer. Now we have to calculate the mass of Mars. There are a few ways to do this. You could do this using centripetal forces and gravitational forces. I don't like to do that. I come from an astronomy background, and the immediate thing that pops into my mind is Kepler's third law here. And I think Kepler's third law is actually easier to do this. Kepler's third law just states that the period squared equals 4 pi, and then depending on what you're looking at for a system. This could be the semi-major axis, but for a circular system, we'll just call it the radius cubed. I'll just give this a bit of a highlight here and put in a footnote. This is normally the semi-major axis if you have an ellipse. And then all we need to do is divide it by the gravitational constant, And then this is the mass of the system. And since our planetary body, Mars in this case, is so much more massive than a little rinky-dinky satellite we're putting around it, we can just really call this the mass of Mars here. Yes, technically it also includes anything else in that system, but this is really just the mass of Mars. I'm not worried about the sun going on here. The only two objects I care about in my system are Mars and the satellite. The satellite's so rinky it doesn't matter. So that means all I have to do, because I have this orbital velocity from part A up here, I just have to solve for the mass of Mars, which means that the mass of Mars is equal to, slight typo, 4 pi squared times that orbital radius, or the semi-major axis cubed, divided by g times the period squared. So we just throw in all of our values here. This will equal 4 pi squared. Our orbital radius we had from part A is 3.83 times 10 to the 6th meters divided by g, which is 6.67 times 10 to the negative 11th. And then the period squared, we know the period from before, that's just the time it takes to go around, 7.08 times 10 to the minus, or times 10 to the, 10 to the positive 3 seconds squared. We just make sure we throw that all properly into our calculator, and we should get a value that is somewhere around 6.63, 6.64 times 10 to the 23rd kilograms. Even if we took out the mass of the survey, the 930 kilograms, it wouldn't matter. That's times 10 to the 23. Like, that's such a big number. That's all we have there. So that's how I like to do this problem. I just like to invoke Kepler's third law, and then I have everything else, so I'm good, and you're done. If we want to get the total mechanical energy of the orbit, this requires a little bit more finesse for us. To get the total mechanical energy in orbit, minus the radius of Mars. No, so if they're looking for, in part A, for the radius of orbit, you don't have to subtract the radius of Mars. In part D, or part E it is, these are talking about above the surface or the altitude. That's when you care about Mars's radius. But at the moment, we don't care about Mars's radius. Whenever we talk about radius of orbit, we're always talking about from the center of that planet. So we don't have to subtract anything off. You can just leave that as it is. This is the value you want right there. Okay? Very common mistake students make. They try to take values off of that, but this is the full orbital distance you want. If we're doing the total mechanical energy in the orbit, then this, like I said a second ago, we have a little bit more issue here. It's important to remember that the total mechanical energy, E, is equal to a combination of your kinetic energy plus the potential energy. And it's also important to remember that we define a point at an infinite distance as being 0 potential, and then as we come in from that infinite distance, we're actually negative. So what we have here is 1/2 mv squared, and then this is minus our gravitational potential energy, which is g m over r. Okay. At this point, we have a correct expression for the total mechanical energy. We've put the negative sign in here. That's 2 points out of the 4 points for this part. At this point, we just need to dump in values and get a number at the end. So if we are dumping in values here, we just need to be a little bit careful. We could algebra this like down to doom, but what I just like to do is I personally just like to throw in the fact that this is the mass of the Surveyor, so that's the 930. This is the orbital velocity, so this is the 3.4 times 10 to the third. This is the mass of the Surveyor, the 930. This is the mass of Mars, which we just found was, some big number, 6 point something, 6.64. Times 10 to the 23rd. And then this R value right here, that would be the radial distance we are away from the Martian surface, which is in part A, which we found to be 3.83 times 10 to the 6th. So if you just throw in all those values and crunch this out, you'll be fine. The other thing that you could do here is, if you so were inclined, you could take this entire expression and throw it in here and then try to reduce things. That seems like a pain in the butt. You already have all the numbers, so just go get an answer. The answer that you'll get here is going to be a negative number, and it's going to be 5.4. If you want to actually write that out completely, 5.38 with rounding, times 10 to the 9th. And then units of that are in joules. It's all right that we have a negative sign for our answer here as a mechanical energy. All this means is that we are at a lower potential than our kinetic energy is making up. That's totally fine there. Okay. For part D, if it's placed in a lower circular orbit close to the surface of Mars, would the new orbital period of the Surveyor be greater or less than the given period? This is kind of just a physics thinking problem here. You don't need to do any large mathematics. It's just asking for a check mark and then to justify it. And we'll just draw a quick picture here to kind of demo this. Here's our red planet. Here's where we were initially. If we came to a more interior approach here, like this, then what would be happening is, as we move closer to the planet, our orbiter has to move faster. If it's not moving fast enough, it will not continue to orbit. It'll just fall and crash to the Earth because that gravitational attraction has increased. So as the radial distance decreases here from the purple to the blue, we have to speed up faster and faster. What this means is, if we're going faster than faster, then it's going to take us less time to cover less of a distance. Both are going faster down here, and there's less of a distance down here, given that this is, a much smaller circumference than the outer circle. So it's going to take less time. You can describe this just in, talking about those two features there. As the radius decreases, both the velocity goes up and the circumference goes down, thus less time. You could also say here that with Kepler's law, the semi-major axis cubed over the period squared, it is a constant, because at that point you only have the mass times the gravitational constant divided by 4 pi r. That is the mass times the gravitational constant over 4 pi squared. Because of this, if we decrease the radius and this remains constant, t must also decrease. So we see it in both ways there, however you like to say that. Last but not least, if the orbit is slightly elliptical, so here's our planet and here is now our orbiter. Let's just make it very elliptical. With its, oh, you know what, that's a really bad ellipse by yours truly. Slightly elliptical. With its closest approach here, even though it looks like it's closer on the edges, and its farthest approach out here, or just kind of wherever. What is the speed at this furthest point here? if the speed down here was 3.4 times 10 to the third meters per second. In order to do this, this is actually a very straightforward problem. You are conserving angular momentum. It is a purely conservation of momentum, and specifically angular momentum in this case. If you recognize this, you've done it. You've won. As a point charge, or not a point charge, excuse me, as a point mass, angular momentum is given by mvr. And the angular momentum at position 1 must equal the angular momentum at position 2. So if L1 equals mvr, it must equal mvr, where this is some second velocity and second position, and these are the first positions. We quickly see the mass goes away, which is very nice. The mass of the rover almost never matters. And our velocity at the second position is just equal to the initial velocity multiplied by some ratio of the positions, where this is R1 and this is R2. They happen to give those to us in the problem to an extent. In the problem, they give us the distance above the surface and this distance above the surface. So what they actually give us is they give us a distance here to here and here to here. But we need to make sure that we include this extra little bit on each side. So when we actually do this for our final answer, and this, Ms. Spadaro, is what you were speaking of a moment ago, it will be V1, which is the 3.4 times 10 to the third. But then for this ratio here that we're looking at, when we multiply this, this is going to be the orbital radius of the planet, which is, what did we find? 3.43 times 10 to the sixth. So it's going to be 3.43 times 10 to the sixth plus, and then the distance R1 above the planet. This is R1, it's the closer side of it, so 3.71 times 10 to the fifth. Divided by, and then once again the distance, the radial distance, or the radius of the planet, excuse me, plus that extra distance it is away, which is 4.36 times 10 to the sixth, or fifth, times 10 to the fifth. That's what we want there. We need to make sure we're including the extra radius of the planet because we are above the surface. This picture is very much not to scale. It's not to scale because these values are 10 to the fifth and the planet itself is 10 to the sixth. So maybe a better to scale diagram would be like, here is the planet and these things are like here, and it's going something like that. That would be a slightly better picture, but whatever. It gets the message across. It's a conservation of angular momentum, and that's what's going on there. The actual number you'll get for this V2 is, oh, what is it? It's got to be close to what we had in the beginning. Oh, but it's got to be going slower. Let's just crunch it all in. 3.4 times 10 to the third times the quantity 3.43 times 10 to the sixth plus 3.71 times 10 to the fifth divided by the quantity 3.43 times 10 to the sixth plus the 4.36 times 10 to the fifth. Boom. That gives us a quantity of, there it is, yeah, 3.34 times 10 to the third meters per second. That's what V2 will be in the end. And that does make sense. We're going slower. We're further out. We've slowed down. That's what's going on there. So all in all, not a bad problem. A little bit of orbital mechanics for you. Pulling back a little bit of Kepler's law, though you didn't need it for part B. And part A is really just thinking about objects going in a circle. I think the hardest part of this would actually be part C here, where we're doing just total mechanical energy. So nothing too bad. With that though, this problem is finished 2007 AP Physics C multiple free response problems got nothing on us. Y'all take it easy and have fun getting a new roof.